So in the last section, we were talking about series. Formal sums of the form summation n going from 0 to infinity, or a0 plus a1 plus a2 plus a3 plus a4 plus ... where these a's were all numbers. The important idea was to determine whether or not this series converges or diverges. The basic idea of convergence was that the successive sums of these numbers were honing in, were decimally approximating a certain fixed number. In the last lecture, we sort of identified 3 ways that we might answer this question. One method was to compute the sequence of partial sums and then find the limit of that sequence. Unfortunately, that's a difficult thing to do because it's actually very, very, very hard to find a formula for these. And without a formula, we can't use our favorite tool, the underlying function test. A second method was to recognize the series as the Taylor series of some function evaluated at a point inside its radius of convergence. But recognizing what function it might be is hard to do, and right now we only know the radius of convergence for 4 functions, e to the x, sine, cosine, and 1 over 1 minus x, and only at the origin. We also argued that if the sequence of terms, the things we're actually adding up, didn't converge to 0, that they didn't get smaller and smaller and smaller, then the series had to diverge. Unfortunately, it doesn't go the other way around. This idea doesn't detect convergence, but it's going to be the start of our topic for today, which is it possible to figure out convergence using only the sequence of terms and nothing else? This is going to be the idea of convergence tests. A convergence test is a method to detect the convergence or divergence of a series an by investigating only the sequence of terms an, but not the partial sums. For example, the statement, or bullet 3 in the last one, the statement that if the limit of the sequence an doesn't converge to 0, then the series an diverges, would be an example of a convergence test. Well, technically speaking, it's a divergence test. This is sometimes, in fact, just called that, the divergence test. It turns out that there are a large number of convergence tests, and a standard calculus book will have many, many of them. A typical calculus book will include a monotone convergence test, a comparison test, a limit comparison test, an integral test, an alternating series test, a root test, a ratio test, an absolute convergence test, and a lot of others. For students first learning calculus, it can be hard to sift their way through all of these things, and so I'm not going to take the approach of trying to teach you all of these. I'm going to take the approach that you guys are training to be scientists and engineers. So what I'm going to do is I'm going to give you a shorter list of convergence tests who can't cover every possible case, but they'll cover the cases you're most likely to see as engineers, as scientists, as people who are trying to understand the real world. And these convergence tests are the divergence test, the integral test, the alternator test, and the ratio test. Our goal over the next 2 topics is to take a look at what these tests are. In this podcast, we're going to focus on these first 3, just to sort of get our feet wet with them. The divergence test says if the sequence of terms doesn't converge to 0, then the series of terms diverges. We'd mentioned this in the last podcast, but it's worth pointing out that if the limit of the sequence is equal to 0, then you can conclude nothing. And we'll say this in the language of convergence tests, that the test is inconclusive. This is one of the reasons why we have multiple convergence tests. But let's see what we can do with this one right now. Suppose we want to investigate the convergence or divergence of the series summation n going from 1 to infinity of n times sine 1 over n. In practice, when it comes to asking a question about series, no one ever goes and attempts to work out partial sums. What people try to do is find the appropriate convergence test and see if they can detect whether or not it converges or diverges first. Let's try to do that work over here. We've got the terms n times the sine of 1 over n. So let's see if we can apply the divergence test, which is right now the only convergence test we know, and take the limit as n goes to infinity of n times the sine of 1 over n. Don't know why I needed that extra parenthesis there. Sorry, that happens. So the first thing we want to do is convert this thing over into an underlying function. Now, I've got to go through and check to see whether or not it is in fact an underlying function. So the first thing I got to do is check for discontinuities. Well, it's only discontinuous at x equals 0. The other thing I got to do is check for the finite number of critical points. Well, that's a problem, possibly, because it's a sine function. Sine are oscillatory. So let me take a quick derivative of this thing and make sure how many critical points it's got. So using the product will be the derivative of the first times the second, plus the first times the derivative of the second, which would be cosine 1 over x, times negative 1 over x squared. So we're going to have sine of 1 over x minus x times the cosine of 1 over x. If we set that equal to 0, we're going to have, well, let's see. No, I'm not quite sure how to solve something like this. But I've always got a machine I could at least go and say, plot it. So we'll plot the function, and I'll plot it on an interval from 1 to 200. Remember, I only care about this function from starting at n equals 1 and on, so I don't really care what it looks like beforehand. Now, if I go and run the command, then we get this graph right here. Now, clearly it crosses the x-axis somewhere between 0 and 1, but other than that, it seems to be growing, or going in a decreasing fashion, which means it certainly looks like it doesn't have any more than 1 critical point on the interval I care about. Let's try to add an extra 0, so that I'm plotting it on the interval from 1 to 200 and see if that changes anything. Nope. In fact, it pretty much looks like a straight line once we get to this point. So I can be convinced this is an underlying function. So now that it only has 1 critical point, we can go back and use the underlying function principle. So if we let x tend off to infinity, we're going to have infinity times the sine of 1 over infinity. And that would be an infinity times the sine of 0. And that would be an infinity times a 0. Since 0 times infinity is a type B indeterminate form, we're going to need to rewrite the function as a single giant fraction. Well, given that the sine part is going to be prepped to sine of x to the negative 1, it makes sense to bring that x down below the fraction bar as well. So we have sine of x to the negative 1 over x to the negative 1. If we plug in infinity, we're going to have sine of infinity to the negative 1 over infinity to the negative 1. Now that's not an indeterminate form, so we're allowed to use our intuition. The reciprocal of infinity is 0, so we have 0 on the bottom, sine of 0 on the top, and that's still a 0 over 0. That makes it type A, and that means we can hit it with the L'Hopital stick. So when we do that, we'll differentiate the top and bottom separately. The derivative of the top is going to be cosine of blank times the derivative of blank. The blank is x to the minus 1. Its derivative is negative x to the negative 2. On the bottom, we take the derivative of x to the negative 1, which is negative x to the negative 2. So our derivative is complete. If we do the cleanup, we see that those two guys cancel. And so we have the limit as x tends to infinity of the cosine of x to the negative 1. If we plug in infinity, that gets me cosine of infinity to the negative 1. We've said that that's 0, and the cosine of 0 is 1. So we've done all of this work to show that the limit as n tends to infinity of the terms of the sequence tend to 1. By the divergence test, if the limit of terms doesn't go to 0, and ours don't, they went to 1, then we can conclude that this series right here diverges. Now, last time, we actually took a look at two different examples. The example of summation n going from 0 to infinity of 1 over 2n, and the summation n going from 1 to infinity of 1 over n. In both cases, the limits of the terms converged to 0. As n gets larger and larger and larger, 1 over 2 to the n will tend off to 0. As n gets larger and larger and larger, 1 over n will tend off to 0. So in both of these cases, the terms tend to 0. But we saw last time that the series on the left converged to 1, and the series on the right diverges. This shows that the test is inconclusive when the terms go to 0. So is there any other way, other tests that we could apply to help distinguish these two cases without looking at partial sums or Taylor series? The integral test says that if a sequence has a continuous underlying function f of x, then the series n going from k to infinity of an converges if and only if the improper integral from k to infinity of f of x dx converges. In other words, the convergence of the sum of terms is equivalent to the convergence of the integral of the underlying function. The actual sum of the series, if it converges, is not given in the integral test. Students like to think that the sum of the series and the improper integral are the same thing, but in fact they're not. However, if f has no critical points on the interval from L to infinity, then the Lth partial sum will be accurate to within plus or minus the integral from L to infinity of f of x dx. Now, why does the integral test work? Well, I can't give you a complete proof, but I'd at least like to give you some idea about why it's true. So the basic idea is this. You've got some sequence of dots. Say this sequence of dots right here. Remember, this is A0, A1, A2. We're assuming that it has some kind of continuous underlying function. And so, since it's an underlying function, it only has a finite number of bends. That means that eventually the graph is going to sort of steady down and just go, say, decrease or increase. So I'm just going to draw it assuming it's been decreasing the whole time. And then you can modify the argument a little bit in order to handle other cases. So why does this result work? Well, imagine for a second we computed the integral from 0 to infinity of the underlying function f of x. Well, we know that that integral represents this area right here underneath the curve. Well, certainly that area would be less than the Riemann sum formed by using rectangles whose left endpoints were always chosen to be these function values. Because the graph is decreasing, we have more area here. So I know that this is going to be less than the area of these rectangles. But how much area is in this first rectangle right here? Well, it's got a height of A0, and it's got a width of 1 unit, because a sequence dots are 1 unit apart. That means the second rectangle has a width of 1 and a height of A1. The third rectangle has a height of A2, and on down the line. In other words, the integral from 0 to infinity of f of x dx is less than or equal to the sum of the series. That means that if the series diverges, and the only way it's going to diverge is it's going to have to blow up to infinity, has an infinite amount of area, well then this thing's going to have to sum to infinity as well, and that means it's going to diverge. So if the area under the curve is infinite, then the sum of the rectangles on top of it is infinite, and we have got divergence. On the other hand, though, what if we knew the area underneath the curve was finite? Well, that means it would have to be greater than this area right here, using the right-hand endpoints. But using the same trick, this is the height A1, so this is the height A1, then A2 would be the area of this piece, A3 would be the area of this piece, and on down the line. If I add A1 to both sides, then we've just shown that A1 plus the integral from 0 to infinity of f of x dx would be greater than or equal to the summation of the an's, n going from 0 to infinity. Oops, I want to add A0 to both sides. On the assumption that this integral right here is finite, well then this is just a number on the left-hand side. The right-hand side has to be, right, I'm adding up a bunch of positive numbers, but if it's less than a finite number, then this had better be some kind of a number too, and that means we have convergence. And so that's more or less the idea behind the integral test. The summation represents an area bounded by rectangles, the integral represents the area by a smooth curve, and they're connected with each other. you might also sort of see if you can figure out why this statement works the way it's supposed to. But I'm going to leave that as an exercise for you. Just modify my picture and start counting right around there. So now that we have this integral test, let's see if we can put it to use on the two series that we talked about just a second ago. Determine the convergence or divergence of the series 1 over 2 to the n and the series 1 over n. So let's focus on this first one right here. In this first series, the terms are 1 over 2 to the n. So if I replace all of those n's by x's, I'd have a function 1 over 2 to the x. And since this is an exponential function, this would be an underlying function. So that means, instead of talking about the series, I could investigate the integral from 0 to infinity of 1 over 2 to the x dx. Or equivalently, the integral from 0 to infinity of 2 to the negative x dx. Note that this function is continuous, but its upper limit is an infinity, which makes it an improper integral. The integral test always gives you improper integrals. So the FTC is not allowed. So what we're going to have to do is integrate from 0 to some point a, 2 to the negative x dx, and then take the limit of that as a goes off to infinity. That's sort of a two-step process. So, step 1, let's focus on the integral. The integral of 2 to the negative x dx, if we prep it, is going to be the integral of e to the negative x times ln of 2 dx. That's just the form e to a constant times x. So the integral is 1 over the constant, 2 negative ln of 2, times e to the constant. And then if we deprep, that's negative 1 over ln of 2 times 2 to the negative x. Of course, we were integrating this from 0 to a, so let's put the limits back on. So when I plug in a, I'm going to have negative 1 over ln of 2 times 2 to the negative a minus negative 1 over ln of 2 times 2 to the 0. And so if we clean that up, that would be 1 over ln of 2 minus 1 over ln of 2 times 2 to the a. So now I have the expression I need to take the limit of. If we take the limit as a goes to infinity of 1 over ln of 2 minus 1 over ln of 2 times 2 to the a, we let a tend off to infinity, that's 1 over ln of 2 minus 1 over ln of 2 times 2 to the infinity. This whole expression right here is now infinite, and 1 over infinity is 0. And so we get a value of 1 over ln of 2. Since the integral of the underlying function converges, that tells us that the series 1 over 2 to the n also converges. But it doesn't tell us what to. Now, even though the integral test can't tell me what it sums to, it does give me a crude starting estimate right here. If I take the first term, 1 over 2 to the 0, which is 1, I know that that's going to be accurate to the correct value to within plus or minus this integral right here. So accurate to within plus or minus ln of 2, 1 over ln of 2. And that would be accurate to within plus or minus 1 over 0.7, which is about 1.4. So that means that the correct value is somewhere between 1 plus 1.4, which is about 2.4, and between 1 minus 1.4, which is about negative 0.4. So I can tell you, guaranteed, that the summation of 1 over 2n is less than or equal to 2.4, but greater than or equal to negative 0.4. We saw, in fact, last time that it was exactly equal to 2. And so this is right where it's supposed to be. If we ever want to get these bounds tighter, then we would simply add more partial sums, and that would simply change the bottom limit. So we've answered the first question, the first series. Now let's focus on the second one. In the second one, our terms are 1 over n. If we switch that over for an underlying function, we would have 1 over x. The only critical point here is that x equals 0. It doesn't have any trig, so it's guaranteed to be an underlying function. So instead of considering the series from 1 to infinity of 1 over n, we can consider the integral from 1 to infinity of 1 over x. Just like last time, well, let's see, this is discontinuous at x equals 0, but that's not a problem in our lower limit. But our upper limit is an infinity, so this is once again an improper integral. We can't use the fundamental theorem. Instead, we're going to have to integrate from 1 to some stopping value a of 1 over x dx. And then when we have that value, we'll take the limit as a goes off to infinity. Now this integral we could bang out by hand. This is just going to be ln of the absolute value of x, evaluated from 1 to a. That would be ln of absolute a minus ln of 1. And ln of 1 is 0. And so we're really going to go and take the limit as a goes to infinity, right? You don't want to forget this guy, of the expression ln of a. So if we plug in an infinity, that gets me to ln of infinity. And we've seen that the logarithm graph grows and grows and grows, and so this is going to be an infinity. And so we can conclude that this integral right here diverges. And by the integral test, if the integral diverges, that means the summation of 1 over n diverges as well. We knew that from yesterday's Taylor series argument, but this one's sort of a much more direct version, and so we can find out that the second series diverges. Determine if the following two series converge. Series A, 1 plus a fourth plus a ninth plus a 16th plus a 25. And series B, 1 plus 1 over root 2 plus 1 over root 3 plus a half plus 1 over root 5, yada yada yada. So, let's focus on root A, or the A series first. In the A series first, we're adding up the terms 1, a fourth, a ninth, a 16th, a 25th. So if we write A as the summation of an, and we can find a formula for the an's, perhaps we can use our integral test. Well, let's see. The numerators in each one of those fractions is always, always, always a 1. The denominators, though, well, to get from 1 to 4, you multiply by 4, but then you're not multiplying by the same thing, so it's not geometric. You're not adding the same thing. It's not arithmetic. But if you stare at these numbers long enough, this is 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And so we're looking at an arithmetic progression of numbers squared. So it's an arithmetic progression of something squared. It starts at 1 and goes up by 1. So there's the geometric formula. So we have the summation n going from 0 to infinity of 1 over n plus 1 quantity squared. If we switch this out for an underlying function, 1 over 1 plus x squared, we see that this is discontinuous only at x equals negative 1. It's a rational function. It's an underlying function. So we could instead investigate the integral from 0 to infinity of 1 over 1 plus x squared dx using the integral test. Well, just like the other examples, it's an improper integral. So what we're going to have to do is integrate from 0 to some stopping point a of 1 plus x to the negative 2 dx, and then take the limit as a goes to infinity. So let's make a quick detour and cook up the antiderivative of 1 plus x to the negative 2 dx. That's actually not terribly hard to go and do. If we just do a simple substitution, we're going to have u to the negative 2. That's negative 1 times u to the negative 1. Now we'll plug in our limits, 0 to a. So when we plug in a, we're going to have negative 1 plus a to the negative 1 minus negative 1 plus 0 to the negative 1, which means we've got 1 minus 1 over 1 plus a. Now I know what I want to take the limit of. So we're going to have the limit as a goes to infinity of 1 minus 1 over 1 plus a. Certainly as a goes to infinity, that's a 1 minus 1 over an infinity, and that gets me a 1. And so we can conclude that since the series is from 0 to infinity of 1 over 1 plus x squared converges, we now know that the series summation n going from 0 to infinity of 1 over 1 plus n squared converges as well. It doesn't tell us what it converges to, and I want to keep driving home that point. It only says, yes, it converges. We could get an estimate on it. If we take the first term in the series, that was 1. If we take the integral, that was also 1. So we know that the first term 1 is going to be accurate to within plus or minus 1, which means that the true value of the series lies between 1 minus 1, which is 0, and 1 plus 1, which is 2. In fact, the correct value of this series is known to be pi squared divided by 6, which is approximately 1.6, and so it fits exactly where it's supposed to be. Now, a question about how you find out that this is pi squared over 6, well, that'll be a story for another time. Right now, we just want to show that it converges and be able to get some kind of crude bounds. So we've handled the first series, now let's handle the second series. So the second series, B, is going to be the summation of some terms Bn. If we can find a formula for the Bn, we would be golden. Well, if you take a look at what's going on here, with a couple of changes, making the first term 1 over root 1, and the second one 1 over root 4, we can see that we're looking at fractions who are the form 1 over root 1 plus n, where I'm assuming that I'm starting the count at 0. If we go through and switch this out for an underlying function, f of x equals 1 over the square root of 1 plus x, then a quick inspection shows that, yes, this is an underlying function, and so we can swap out the series for the integral from 0 to infinity of 1 over the square root of 1 plus x. Just as in the previous problems, we have an improper integral, so we're going to have to integrate from 0 to some stopping point a of 1 plus x to the negative 1/2 dx. I'm already prepping it. And then we'll take the limit of whatever we get as a tends to infinity. So let's do some quick side work here. If we integrate 1 plus x to the negative 1/2 dx, making a simple substitution, this will be a u to the negative 1/2, which integrates to 2 times u to the 1/2. We're going to integrate that from 0 to a, so let's swap or put on the limits. We plug in a, we're going to get 2 times 1 plus a to the 1/2 power. Minus, we plug in 0, we're going to have 2 times 1 to the 1/2 power, which is 2 times the square root of 1 plus a minus 2. If we take that information and plug it back into here, we now need to compute the limit as a tends to infinity of the expression 2 times the square root of 1 plus a minus 2. If we let infinity go into there, we're going to get 2 times the square root of an infinity minus 2, but that's a giant number. And since we get an infinity, we know that this limit diverges. So the integral from 0 to infinity of the function f of x dx diverges. By the integral test, that means that the summation n going from 0 to infinity of our function bn, root 1 plus n, 1 over that, also diverges. And so in this case, our second series diverges. Both of the previous examples were special cases of series of the form 1 over n to the p, n going from 1 to infinity. So 1 plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, down the line. In the previous example, we looked at the case when p equals 2 and found that it converges. And we also looked at the case when p was equal to 1/2, when we had the square root functions, and we found that that diverges. We also might notice that p equals 1 is a special case of the harmonic series, 1 plus 1/2 plus a third plus a fourth, which we also know diverges. Turns out that these kinds of series pop up not infrequently, and so they're given a special name. They're called the PSeries. The idea being, well, there's this power p running through here, where p is short for power function, because we're looking at, well, x to the p for all intents and purposes. The last example is supposed to give you some idea that if we apply the integral test, we find out that a p-series will converge provided p is greater than 1, but it diverges if p is less than or equal to 1, which you can check out with the integral test on your own. The one thing I want to point out about this is that while the integral test tells me what they sum to, most of the values of the p-series are unknown. When p is equal to 2, that's the sum 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. I'll get it if you give me enough time. The great mathematician Leonhard Euler, he of the number E fame, actually used a fairly sophisticated Taylor series-esque argument to show that this series converged to pi squared over 6. He was also able to show that for the p equals 4 powers p series, so 1 plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th, that series, which we know converges from the line above from the integral test, converged actually to pi to the 4 over 90. In fact, he was able to work out formulas for 6 and 8 and 10 and all of the even ones by, like I said, a fairly sophisticated Taylor series argument. But to this day, no one knows the value of the p equals 3 p series. 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed. We know it exists. We can figure out what it is approximately equal to, but no one knows what this thing is to this day. So you're actually right now at the frontiers of mathematics when you're just playing around with p-series. It's worth pointing out that students often get this confused with a related series. And that would be the series n going from 1 to infinity of 1 over p to the n, as opposed to 1 over n to the p. So that's the series 1 over p squared, 1 over p cubed, 1 over p to the 4th, dot, 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 dot. It turns out that this guy right here is not a p-series. This is actually a geometric series. And you might be able to see it if you pull out the extra 1 over p common to everybody. When we pull out the extra 1 over p, then we have 1 plus 1 over p plus 1 over p squared plus 1 over p cubed. And that's nothing more than the geometric series 1 plus blank squared plus blank cubed plus evaluated at 1 over p. Now we know that the geometric series has a radius of convergence of exactly 1. So as long as this fraction is less than 1, which means that p is greater than 1, then we know that this series sums to the geometric series function 1 over 1 minus blank, evaluated at 1 over p. So if we distribute the p through, we're going to have 1 over p minus 1. So on a geometric series, we can actually work out the sum every single time. On the p-series, well, that's a new math problem for you to solve. Now both of these examples, together with the previous ones, fit the case of having an underlying function. But what if the terms of your series don't have an underlying function? Well, depending on what those terms might look like, I may have a test for you. The Alternator Test says, suppose that you have a series an whose terms can be written in the form -1 to the n times bn. You might remember when we were talking about series that this thing was sometimes called the alternator because it caused sign changes. Well, if the other part, the non-alternating portion of that series, bn, has an underlying function, then the original series an converges if and only if the limit of the non-oscillating part converges to 0. Now, just like the integral test, the alternator test cannot tell you what the series sums to, but it can give you an error estimate. If the underlying functions for the sequence bn is monotone on the interval from L to infinity, remember monotone just means it's decreasing or increasing only, then the Lth partial sum will be accurate to within plus or minus BL plus 1, which is the next term in the series. And so this gives us a useful way of gauging the accuracy. To give you some idea about why this thing works, imagine that you had a series of the form -1 to the n bn. So that's going to look like b0 minus b1 plus b2 minus b3 plus b4 minus dot 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 dot. Now remember, the sequence bn has a nice underlying function. And what that means is, if I draw a smooth connecting curve through them, it's only going to have a finite number of bends. So eventually it's always going to be, say, decreasing. And for convenience, to make it the point easier to illustrate, I'm just going to draw it always decreasing for my terms. What I'd like to do is I'd kind of like to illustrate what the sum is doing by sort of looking at their y distances. Here's b0, or b0. Here's b1. Then we have b2, and then we have b3, and then we have b4, and then we have b5. Now, imagine I laid out this length. Here's the length b0. starting at 0. But then when I add the first two terms, I'm going to go backwards b1. And so this point right here represents b0 minus b1. But then I'm going to add b2. And so that's going to put me right here. But then from that, I'm going to subtract b3. And that's going to put me right here. Now, as I go back and forth adding and subtracting and adding and subtracting and adding and subtracting, sooner or later I'm going to end up at some fixed spot. And that's what the sum of those bn's is going to be. Because I know they're getting closer and closer and closer together, the wiggle room is getting smaller and smaller, and sooner or later, bam, I hit a value in the middle. That's at least the heart and soul of the alternator test. So let's try it on an example or two. Does the series summation n going from 1 to infinity of minus 1 to the n, 1 over n, converge? Now if I actually write out what that series is, that would be negative 1 plus a half minus a third plus a fourth minus a fifth plus a sixth. Which looks an awful lot like the harmonic series 1 plus a half plus a third plus a fourth plus a fifth, which we've seen now twice does not converge. What will the effect of putting these plus or minuses do? Well, let's find out. Each one of these terms in the series we're looking at right now takes the form minus 1 to the n times 1 over n. So they take the form of the alternator times some other sequence. That guy right there is our bn, the 1 over n. Now bn has an underlying function of 1 over x. 1 over x is discontinuous only at 0, doesn't have any other oscillations, and so we know that this is an underlying function. So to use the alternator test, instead of working on the series, let's just take the limit as n goes to infinity of the non-oscillating part bn. That would be the limit as n goes to infinity of just the 1 over n portion. We switch over to our underlying function. That's the integral from, the limit as x goes to infinity of 1 over x. That gets me a 1 over infinity, and that gets me 0. So we've just shown that the terms converge to 0. By the alternator test, that means that the series n going from 1 to infinity of negative 1 to the n, 1 over n, converges. Once again, it doesn't tell me what it converges to. All it can do is say, yes, we have convergence. But I can get some bounds on what the value is. For example, if we took the first term, negative 1, that's an approximation of the sum, and it's going to be accurate, according to our formula, to within plus or minus b2, the next term. So it'll be accurate to within plus or minus 1/2. So that tells me that the series negative 1 to the n, 1 over n, is going to be less than negative 1 plus 1/2, which is negative 1/2, but greater than negative 1 minus 1/2, which is negative 3/2. In fact, it turns out that this value is exactly negative ln of 2, or negative 0.7, and that puts it square where it needs to be. Once again, how do I get this value? Well, that's going to be a story for next time. Does the series cosine n squared pi over n squared pi converge? Well, let's see what tools we've got in our arsenal. This takes the form summation an, where an is equal to the cosine of n squared pi over n squared pi. Now, if we switched all of those n's to x's, we'd have cosine of x squared pi over x squared pi. But unfortunately, this thing's not going to be an underlying function. Because although it only has one discontinuity at x equals 0, it's really a giant cosine function. And if we plot this function using, say, Maple, we're going to see that it has an infinite number of critical points. It bends over and over and over again. See what I mean? So without this underlying function, we can't apply the integral test. So the integral test is out. But let me actually go and write out what some of these terms are. This is going to be the cosine of 1 pi over pi plus the cosine of 4 pi over 4 pi plus the cosine of 9 pi over 9 pi plus the cosine of 16 pi over 16 pi plus dot 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 dot. But each one of these numerators is just a trig function evaluated at a standard angle. The cosine of pi is -1, so this becomes -1 over pi. The cosine of 4 pi, well, cosine of 4 pi is the same as cosine of 2 pi, is the same as cosine of 0, which is 1 over 4 pi. The cosine of 9 pi, well, cosine of any odd multiple of pi is -1, so we've got -1 over 9 pi, plus 1 over 16 pi, minus 1 over 25 pi, plus plus plus. So even though the original series didn't look like it, we are in fact staring at an alternating series. The summation, n going from 1 to infinity, of cosine of n squared pi over n squared pi is nothing more than the summation n going from 1 to infinity of -1 to the n, that's the plus minus, times 1 over n squared pi. And so this takes the form that the alternator test is comfortable with. I've got the alternator out in front, and that means this is my Bn. So if we can show that the limit as n goes to infinity of the Bn terms, the n squared pi under 1, tends to 0, then we're golden. But we can switch out all of the n's for x's. That gets me 1 over x squared pi. This is just a basic power function, so it has but one critical point. So we can apply any of our Calc 1 tools. We're going to get a 1 over infinity, which is a 0. And so since the non-oscillating part tends to 0, we can conclude that the series converges. So, to answer this question, does the series converge? Yes, by the alternator test.